I want to welcome everyone to this webinar series. This is the second session of an ongoing series that we are delivering for some weeks now. Our previous session was dealing with the solar PV development in the state of Maryland. You can find a copy of that webinar from last week on our website. The web address is listed on the slide I've shared with you. So you can find that there. Today's topic is dealing with the basics of solar PV technology. We'll look at some components and types of systems and start to navigate how we can use this. Primarily, of course, this is geared towards agricultural use. But what you'll find with this webinar today, as well as subsequent webinars, is very practical for residential and commercial and other applications as well. So just bear that in mind. We will kind of talk about this in the framework of an agricultural setting, both from a small scale and a larger, even up to a utility scale system. So before we really dive into the content of this webinar, I'll just provide a brief introduction of who I am. My name is Drew Chavone. I'm an extension specialist with the University of Maryland. My background is actually in agricultural engineering, and so I'll bring some of the kind of engineering perspective to our webinar today. I'll try not to get too entrenched in the mathematics or other aspects like that, but we'll cover some very practical tools that will help us understand how solar PV can be developed and implemented. My work primarily deals with energy conservation and clean energy technology. Of course, that's including solar photovoltaics like we're talking about today, but if you're interested in more about solar PV or other energy topics relevant to the state of Maryland, you can go to our website again and find some more applied research and programs like you're joining today, and you can get some more information on those issues. With that said, let's go ahead and talk about what our program is today. So I'm going to advance in the slides. As I mentioned, the Zoom format today might be a little bit different. Your screen might appear a little different than what I have, but you should have a Q&A section towards the bottom. At any point in time, please input your questions that you might have through the course of our webinar today. And at the end of the hour, I'll do my best to address some of those questions. Of course, you can reach out to me directly as well. Once we wrap up our program today, my email and phone number are provided on the slides, and you can get that on the website as well. So just to know, and again, I'll remind us that this session is being recorded, much like our last week's session was, and those will all be posted to our YouTube feed and on the website as well. So with that said, let me issue our first survey, and I just want to launch this survey to provide for you guys to provide some feedback on who we have joining us in our program today. And so the first question, there's two questions here. The first question is, what sector of industry are you from? Some options there. Please select one or more of those options if you're a homeowner, if you are a farmer, whatever that may be. Question two is specific topics you might be interested in. Rooftop solar, electric fencing, whatever that is. You can select multiple options, and when you're done, don't forget to click the submit button, but that'll help me just understand who I'm talking to on our webinar today. So I'll give you 1 minute or so to put your answers in there. It's great. Seems like we have a pretty good mix. We have a lot of farmers joining us, homeowners as well. So a little bit of mix there, and a host of other industry. And we'll give you about 10 more seconds or so to complete that, and then we'll move on with our program today. Okay. Well, thank you for your input there. We'll take a look at what the webinar today is really going to focus on. And first of all, we'll go into a science lesson, and to some extent on electricity and circuits. Like I said, we're not going to get too into depth on some of these topics, but just having an understanding of power and energy is going to be very valuable moving forward in not only this webinar, but if you're able to join us for any of subsequent webinars, it'll be helpful to know some of these terminologies that we'll cover. And then we'll get more into the specifics of the solar PV technology and systems. Now, we'll start just recapping and expanding on some of what we mentioned in last week's webinar, talking about electricity as the form of energy that we're going to focus on. Now, electricity is very practical for many different applications, whether it's lighting, heating, whatever it may be. There's a lot of applications for it. And of course, electricity is what's generated from a solar photovoltaic PV system. And so that's really what we're going to talk about is electricity generation. And this was mentioned, a topic was mentioned last week about how a lot of the conventional energy sources that we use, things like natural gas and coal, or even renewables like wind and hydropower, they all kind of work with a turbine system. Now, solar PV obviously stands out because there's no turbine associated with solar PV, but this is kind of a distinction, again, to make between how solar PV generates electricity and how conventional systems. In a conventional system, you typically have that turbine that's being spun around by something, and that drives the generator. Essentially what that is just a wire moving across magnets. And so as that wire moves across the magnets, you have an induced current. Electrons start to flow through the wire. And that's really all there is to it, is that flow of electrons. That's what we define as electricity. As I mentioned, that is different than how a solar PV system operates, and we'll touch on that momentarily, just so you have a basic understanding of what electricity is, driven by those magnets and that flow of electrons. I'll touch here on a couple key terms that we need to recognize. Again, not to get into too much detail, but I do want to make a distinction here between direct current and alternating current. Direct current is when the electrons flow in a single direction. This is the type of flow that we're going to experience with solar PV systems as well as battery systems. If those systems are generating that current or delivering that current, it has to be transformed into alternating current for use in, you think of the outlets in your house, for instance. They're working off alternating currents at 120 volts, so you're going to have some difference there. You cannot plug in, a standard light bulb directly into the direct current because they're going to be different applications. We'll talk more specific about that, but I just want to, at this point, emphasize the difference between direct and alternating current in terms of PV being your direct current and most of our uses, and we'll call that our load. A load would be anything like a lamp, a light bulb, anything that you plug in that uses electricity, pump, motor, whatever it may be. So those systems typically have to operate off an alternating current, and so we'll see the transition is important going from a direct current to alternating current, and particularly we'll look at the role of the inverter in that process. What I think is practical here as well is taking a look at the terms voltage and current. These two terms I think many of us are probably familiar with to some extent. And what I find helpful in understanding the voltage and current is using the analogy of water moving through a garden hose. And so if you think about it, the pressure, the force with which that water is moving through the garden hose, it's kind of like the voltage, that pressure, that difference of pressure pushing through the wire, that would be your voltage. The current, on the other hand, is like the flow rate, the speed that it's going through the hose. And so you can imagine, different size hoses, you're going to get different flow rates. Well, the same thing with different wires and cabling, you'll have different flow rates of current. So those are two differences. Voltage is measured in volts, of course, and current is in amps or amperes. You can use common tools like what I've indicated on the slide presentation. If you can see that, make out those photographs there. Just using a multimeter, for instance, to measure the voltage. You'll see one example there, looking at the alternating current in a house. So going right into the wall socket, you should have about 120 volts on it, whereas a car battery if you're measuring DC current, direct current, you're going to have it more in line with 12 volts. So there's some difference there. Again, those two systems are operating a little bit differently. But yeah, there are a lot of tools. Many of you are probably familiar with those tools and handy with those. For others of us that may not have used that too much in electrical work, we'll have some more hands-on programming going into 2021 next year. We'll probably do some more training with that as it relates to solar PV. But that's something just to keep in mind. Now here's something that's absolutely critical for us to understand. It's the difference between power and energy. And I think rather than regurgitate a definition, I think using the example of the light bulbs, that illustration at the bottom of the slide presentation, if you consider this example, I think it makes a lot of sense, or at least it does in my mind. So if you're talking about power, that's something that when you go to the store and you buy a light bulb, the power rating is stamped. And in the case of a light bulb, it's usually stamped right on the light bulb itself. And the power is measured in watts, typically in watts. Could be kilowatts as well. But in this example, we're going to say that I purchased a light bulb for 100 watts, and that's the power of it. But the energy implies that it's being used for some amount of time. So in the example, I said that the light bulb is turned on for 3 hours. So in this case, you can take the power, 100 watts times 3 hours, and that gives you the energy use for that light bulb. So after 3 hours, you've used 300 watt hours. That's the units of energy that we're going to talk about for the purpose of this program, is watt hours or kilowatt hours, but the same concept there. So when you receive your utility bill, if you're connected to the grid, which most of us are, if you're getting grid power, your utility provider will send you a bill and you'll be charged for how much energy that you have used. It really doesn't matter if you have a lot of small light bulbs or a lot of big light bulbs, whatever the power of those light bulbs may be, you're really just, what you're billed for and what you're paying for is that energy usage. And so we'll navigate some of this, but the other important aspect is that when we know the energy of our load, in this example, our load is a light bulb, when we know that energy use, we can start to compare that to the energy that we get from the sun. And so through the course of our webinar today, and even in subsequent webinars, we'll start to bridge that gap between how do we get from the load of energy that we're using to how much solar resource we have available. And of course that happens through a PV system in our case. I've included a couple examples here, just ways that you can determine your power. And this is kind of at a basic level, but we'll just touch on it at this level at first, and we'll get a little bit more in depth as we move forward. But in this example, there's I think a microwave on the left-hand side. And if you take a look at the back of most of your appliances, or you could have an owner's manual or something, and it will specify what the power is. So on the microwave on the left-hand side, you see that I've highlighted it is 330 watts. That's the power. Now I've also included another example on the right-hand side. And in this case, on the right-hand side, there's no indication of the power. There's no wattage given. And so what this requires is a little bit more work. In this case, we can clearly see that it's 120 volts is the voltage. And then if you look a little bit down the line there, you'll see 3.5 amps, which is our current. So they do give us the volt and current. If you didn't have that, you'd have to go back and measure it manually with some kind of multimeter or something like that. But at least we have this printed on there. And in this case, I alluded to the fact that we're going to use a little math, and here it is. So the math behind this is just multiplying your voltage times your current. So it's not too hard. You might have to pull out your calculator to do this like I did. But if you say 120 volts times 3.5 amps for your current, that gives you a power of 420 watts. So again, this is a very simple way that we can evaluate the power of any system. Another example of a clothes dryer. For the clothes dryer, it in this case is 220 volts at 8 amps. Multiply those two numbers together and that gives you your wattage. Now we can do the same kind of bit of information on the delivery side with the PV system itself. If you look at this module on the right-hand side, this operates at 40 volts up to 5 amps, and we can multiply our 40 volts times 5 amps. If you run those numbers, it's 200 watts. And so this says nothing about the energy necessarily. We'll get to that point. But this is kind of the first step, is evaluating the power of the system. Now, what I'll say, you might be thinking, why is this all important? Well, a solar module is able to produce a specific amount of power based on how much sunlight we have. And the sunlight is obviously highly variable. If you go, not only day and night cycles, but seasonal cycles. If you look in the summer, you're going to have more sunlight available than you will in the winter. You have weather patterns and other things, cloud cover. So it's a highly variable resource, and it's hard to kind of quantify just on a power level. So what we're typically looking at in terms of the sunlight, the available power from the sunlight, we're looking at over a period of time. And so whenever we're considering time factored into that, that's really, in essence, what we know as energy. So we're looking at energy over time, and it might help to sum this up over time. I've included a couple examples here. If you're looking, month by month, like as I mentioned, in the summer months, you're going to have a little bit more energy available from the sun, but oftentimes it's easier to provide a summation over the whole year or something like that. But we'll get some more examples, practical examples, as we go forward. The whole idea is, again, just to get an idea of the energy from the demand side, the energy that you're using, and then compare that to how much energy is coming from the sun. So here's two additional examples. Now, with these examples, we're going to look, obviously, this is the load side, the energy that we're using. And if we look at it from this perspective, we're going to calculate the amount of energy that we use over the entire course of a year. Now, this is a very basic, guesswork at how much energy we use. We do have tools and resources on our website that'll help you evaluate your energy use more accurately. But this is a good estimate. And so I've pulled two examples. One is a motor here, much like the one I have on my table saw. The power for this is about 600 watts. But to determine how much energy that motor uses, you have to guess how long you're going to be using it. So in this case, I've estimated that I use this motor about 15 minutes a day, which is a quarter of an hour. And the annual use, I don't use this every day, but this motor is activated about half the days of the year, 180 days. So again, here we're taking our power and we're factoring in how often we're using the equipment. And so 600 watts times that usage gives you 27,000 watt hours of energy. 27,000 is kind of a large number. So kilo is 1,000. And so we can just divide that 27,000 watt hours by 1,000. And that's a little bit easier for us to report that number as 27 kilowatt hours. Again, this is what you'll see the units on your utility bill is in kilowatt hours. If you take a look at the other side, the other example here, you'll see a light bulb. In this case, I've selected a light bulb of only 60 watts. As you can see, the power of this light bulb compared to the motor is much smaller. Power is only 60 watts compared to the motor, which was up at 600 watts. But it's not the power that really makes a difference here. We're going to, again, calculate the energy for the light bulb, how often you use it. And so this is kind of a conservative estimate that the light bulb is on 4 hours a day. In my house, that's kind of a conservative estimate. I always have to go around behind my kids, turn on the light switches off, but that's another story altogether. What I will say is 4 hours, again, kind of a conservative guess, but 4 hours a day, and you're going to use that lighting almost every day of the year, 350 days. If you run the calculation on that, you get 84,000 watt hours. Okay, so again, you could just use kilowatt hours for that. That's 84 kilowatt hours. But what I want to point out is just the importance here of understanding energy and not just the power of the system. Energy, you'll see the light bulb had a lower power rating, but because you're using it on a much more frequent basis, your energy consumption for the light bulb far exceeds that of the motor. So we'll start to see how that's important. Now, to pivot and look at the production of that electricity, we'll look at a PV module or a PV output here, and it follows the same kind of format. Again, this is just an estimate. We're not going to rely on this data to invest in, but this is good back of the envelope calculations. So we start step one, just looking at the power of the system. Again, that goes back to the voltage and the amp current rating of the panel. In this case, it's about 215 watts. And then we'll just make a ballpark estimate that on average through the course of the year, we're getting that output for 4 hours a day. Again, this is just a rough estimate. And then 365 days a year, assuming we're getting at least that amount out of it for 4 hours. So you run the numbers on that, and that comes out to 315 kilowatt hours. So that's just kind of a ballpark and how we start to line those numbers up. Now, as I mentioned, this is a rough estimate. We'll get more specific as we go forward. But I do want to make sure we have time to touch on some of these other aspects. Before we jump into the next section, I'm going to launch an additional poll here. This poll is to kind of capture your level of understanding of some of the topics that we'll address today. So question number one is just assessing what your interest is in participating in our webinar today. Question two, you might have to scroll down to see that. Question two is to assess your current level of understanding. And hopefully by the end of our webinar today, you'll get a little bit of a better understanding of some of these topics. Just indicate this is an anonymous poll, so I won't be sharing it with anyone, but just to see where you're at now. So I'll give you another minute to wrap up your question, and don't forget to click the submit button towards the bottom, I think. About 10 more seconds or so. Okay, thank you. I'll go ahead and end that poll. Appreciate your input on that. Now we'll jump into more of the specifics here of what a PV cell and module is. We'll kind of get an understanding of how those systems work. They work very different than our conventional electricity generation. And so we'll touch on that, and we'll look at some of the systems towards the end of our hour here. So a quick overview of the technology. The cell is the basic building block that a manufacturer produces. But for us on the consumer end, we're going to be purchasing the whole panel, or what you'll see here is it's denoted as a module. You can use those terms interchangeably, the panel or the module. And so the module is made up of a lot of those little cells. It could be 36 or 60 or 72, whatever it may be. And you'll probably, as in the example shown here on a rooftop system, you'll probably need more than one panel if you're working with a bigger system like this. And that in case would be called a solar array. So just so you're familiar with some of those terms. Now the PV cell, again, this is the basic unit. For the most part, these cells are about half a volt. And just in comparison, and we're talking about silicon cells here. There are other materials that can be used, and I'll kind of touch on those, but we'll spend most of our time talking about the silicon-based PV cells. This is the most widely available and utilized material for solar energy. But if you consider most of these cells are around half a volt, a AA battery is about 3 times that, 1.5 volts, just to give you an idea of the voltage involved. What it is, it's just essentially a big slice of silicon, and it's overlaid on the top and bottom with electrodes, these contacts that help the electrons flow. That's on a very fundamental level, but we'll just leave it at that for now. As I mentioned, silicon is the most widely utilized. It's the most widely available. There are several different types of that. The most prominent ones are your mono and polycrystalline. I'll just make a couple notes here. The monocrystalline is a much higher efficiency. Well, not much higher, but quite a bit higher efficiency at turning solar energy into electricity. As such, the monocrystalline, although it's more efficient, you can imagine it does cost quite a bit more. Polycrystalline is probably one of the biggest shares of the market right now, produced to the highest amount. Its polycrystalline is not as efficient as the mono. Its production is a lot easier than the monocrystalline. You can tell the difference between the two just by looking, the shape of the cells and the appearance of it. The polycrystalline, for instance, if you had a better resolution or a panel in front of you, you'd be able to tell the shiny, flaky nature of the polycrystalline, whereas the monocrystalline is very pure and smooth. There are other technologies like thin film. These use various materials. There are some silicon-based thin film. Some of them are flexible and you can bend and warp them. Some of them are more rigid. And so I'll make a couple comments on that, but just on a basic level, understanding the efficiencies, I think has some value. So amorphous silicon, we'll start just with that example. Amorphous silicon is a thin film technology. It's not very efficient, and you're not going to see it outside of applications like typically outside of little things like this, a calculator. But more in tune with what we'll be implementing on farms and homes and commercial operations is the poly and the monocrystalline silicon. Again, the mono is more efficient. You can see some of the production steps that go into that and forming, starting with a seed crystal and then forming a large solid ingot. And then that ingot gets sliced up to form those monocrystalline panels. So it's a very intense, energy intensive process. One of the reasons that it's more expensive is because of that. But if you can align the numbers where that monocrystalline is more financially viable for you, that could work out because it does have improved efficiency over the standard polycrystalline. Now, how this technology works, the silicon is basically a semiconductor, and I'll talk just briefly on how that works. If you look at the cross section here of that silicon, you see the top contacts, the electrodes on the top, but the bulk of that material is silicon, which again works as a semiconductor. Typically, the silicon is doped with some kind of impurity. Typically, the phosphorus is a negative charge, and the boron is what's typically used for the positive charge. And so when you have these impurities mixed into the silicon, what happens is the solar energy, when that photon of light comes down from the sun, it excites the surface, the negative type, and you get an electron released into the circuit. And so you can see follow the pathway there, the clockwise motion of electrons going to that light bulb and then refilling in from the bottom of the silicon panel. So again, just a basic overview of how a semiconductor works. Clearly, as I mentioned, that's different than your turbine generator system, but that's the essential nature of a PV cell. I mentioned there are other materials out there. I'm not going to touch too much on these. These are more of research and development stage, so you're not going to see a whole lot of these types of systems on the market today. Some of those would be the SIGs and the gallium arsenide. So there's materials out there besides just silicon, but these are, as I said, at the research stage, going to be quite a bit more expensive as a result. The multi-junction, I'll say, multi-junction, it's kind of a neat technology where you're creating layers of different materials. And so you do get the benefit of multiple layers, but you're also paying for that additional development there. If you're interested in some of the other technologies, you can look at the a report put out by the National Renewable Energy Lab. They report for a number of different technologies out there, primarily in the research stage. What I will point out is that, again, that multi-junction, that purple line shows how the efficiency has improved over time for the multi-junction, in some cases exceeding 30 and 40%. But again, most of our poly and monocrystalline are down between 15 to 22% efficiency. So we're not quite where the potential is for that market, but sometime down the line, you might see more of those innovative technologies hit the market. So what we do with the PV cells, again, the PV cells are those smallest units that are manufactured. And again, they're typically around half a volt. So what the manufacturer does is start to string these together in series from the negative terminal to the positive terminal of the next. And in this example, I've just put 8 of them together in series. And so you sum the voltage over that whole series. So if you add those voltages up, in this example, you get 4 volts. An example of this that you might be familiar with is just putting your batteries into a flashlight. So in this example, you have 2 batteries, negative to positive terminal in series. Those 2 batteries are summed up to a total of 3 volts. So that's the same kind of concept there. Now, what happens with this at the manufacturing stage, they create that series of PV cells. They put it, laminate it on a backing material. They seal it with weatherproof plastic coating, and they cover, put a glass cover on the top. And typically you'll have an aluminum frame around the edges of it. You could use other materials as well. Aluminum's pretty affordable and most common. You could use steel or other things under extreme environments, but for most of our applications, you'll see aluminum framing. That's the basic fabrication process of it. Now, we'll pivot at this point and start to look at the resource that we get from the sun. As I mentioned, there's a lot of variability in the solar resource, but we need to kind of understand how we quantify this so we can know how efficient a PV panel is. And so I'll just share this example of the difference in solar irradiance from the winter in January to July. You'll see there's a lot more solar irradiance. And what solar irradiance means is it's really an instantaneous intensity. So at that moment, you're having quite a bit of sunlight in the summer, whereas in January, it's not so high. And so you do have seasonal variations, you have day and night variations, and even weather variations within the day. It makes it all kind of hard to quantify some of these parameters. There is one similar expression, and we won't spend too much time talking about this, but solar insolation often gets confused. I'll just make a distinction quickly here, but solar insolation takes into account a period of time. And so you're taking out the variation that you see over time dealing with weather patterns or seasonal variation. So again, that's one way to look at it. But what I'll say is when the manufacturer has developed that panel, it goes through testing procedures, and this is done at what's called the solar standard or standard test conditions, STC. And this is important for us that all panels go through this evaluation at the same conditions so that we have a good comparison between the systems. We want to know if panel A is better than panel B. And if you think about it, if you test one panel right now at 1 o'clock in the afternoon, it's getting a lot of sun. But if you test your second panel, if you wait till midnight tonight, it's not going to be tested under the same conditions, and the efficiency is going to look a lot worse because of that. So again, here's the importance of having standardized conditions. And there's a couple factors that I'll mention that are a part of this. It's tested at 1,000 watts per meter squared. So again, what you'll see embedded in this is you're looking at a certain space on the ground, 1 meter by 1 meter or 1 meter squared. Not all of our panels are that size, and so we'll have to account for that. But again, this is just the standard. Temperature is also a factor of the standard solar standard, 25 degrees Celsius. And the reason this is important is panels operate at different efficiencies based on what temperature it is. The higher temperatures impact your voltage, and as a result, you get lower efficiency at those higher temperatures. And another expression, air mass, which includes clear skies and humidity and other factors. We don't necessarily have time to get into all that detail today. But this is what most panels are tested on under these conditions. You could certainly test a panel under other conditions. You're just going to have efficiency that's not been tested at those same levels. And so you could use, example here, I've put a little picture of a pyranometer where you can measure solar irradiance. That might be useful for various applications. It's a pretty handy tool to have around if you're working with solar PV. But I'll just point that out. You could measure your system at a different condition, but it's not really going to be able, you're not going to be able to compare. You have to make sure that your panel is compared to that same solar standard. So what do we do with this? We'll look at the efficiency of panels now. And what we'll see is efficiency is just a ratio of the power coming out of your PV system to the power that's going into it. So the power that's coming out of your PV system really is relative to how good your panel works. Whereas you look at the bottom of your ratio, your power input, that is relative to the solar irradiance. And so we have to understand both aspects, and we'll go through an example here of how we can actually calculate efficiency. So I've pulled one example. I don't know if you can make out the details from the solar panel. I took a picture of this. It's a panel, the back sheet, spec sheet for a panel. It's got a number of factors listed on it. I've retyped those on the left-hand side, but the numbers that you get off of that would be the maximum power. You would get the voltage and the current, both at maximum power. Of course, those are all related. Remember, voltage times current gives you power. But what you'll see, and what that panel, that spec sheet emphasizes, is those are conditions that have been evaluated under the solar standard. And so you'll see that on every PV system, every module is going to have that solar standard. And that's important because you could make it look better if you tested it under better conditions, or you could make it could look worse if you tested it at midnight. But again, it's all evaluated at that solar standard. There's some other factors on there: the open circuit voltage, short circuit current under no load conditions. Those are a little bit beyond what we want to touch on today, but we'll just take a look at some of those primary factors and how those are used to calculate the efficiency. Your spec sheet might have other bits of information on it. This one has temperature and voltage impacts and things like that listed. Again, going back to the temperature, at higher temperatures, you're going to have lower voltage, and your efficiency is going to be impacted by that. So sometimes these manufacturers will have that information provided right there for you to reference. That's why it's good to have additional tools on hand when you're working with these systems, like a non-contact infrared thermometer. So you can see the temperature of the panel, you can see other things with a multimeter and measure the voltage and current of your system will be practical as well. But to get into the example here, we'll do two steps here. First is to evaluate the power of the PV module. Okay, so in this case, I have the graph or the chart right from the back of the PV panel. In this case, the power is already specified as 232 watts, but you can check their math just by multiplying the voltage times the current. So 30.1 volts times 7.7 amps. Sure enough, that's the voltage they're reporting. And again, that's at standard test conditions, as noted on the spec sheet. Step two then is to look at the efficiency. And again, I mentioned this earlier, but efficiency is the ratio of the power output and the power input. Okay, so to start with the power that's coming out of your PV system, we just calculated that it's 232 watts. But here's the thing that often trips people up. You have to take into account the size of the panel. The size of our panel is different than what the solar standard uses. And so we have to factor that in. You could measure this manually with a tape measure, or in this case, I just pulled the numbers right from the spec sheet. It gives it in millimeters, but I'm using meters. But the same idea. The area is just the length times the width, 1.62 square meters. Okay, you have to factor that in because, again, the solar standard is based on 1 meter squared, but our panel is a different size, so remember that. You can always go back to this this example if you get it, if you're at a loss on that. But that's your top part of your ratio. On the bottom is simply that solar standard. Again, that's 1,000 watts per meter squared. Okay, it's a pretty easy round number to remember if you forget. But you'll divide those numbers, and in this case, your efficiency is 14.3%. If you compare that to what the manufacturer is stating, they said 14.2, so there's probably a little bit of rounding difference, but the same idea. That's how efficiency of panels is calculated, and it's going to specify that that's at the solar standard. Again, if you test it at conditions other than the solar standard, your efficiency is going to look a little bit different than that. Okay, now we're going to move up to the size of an array, because in a lot of applications, a single panel is not going to provide enough power and energy for your needs, and so you'll look at tying multiple panels together. And this is an example of putting multiple panels into a series. Again, negative to positive terminals, and again, you just add the voltage up. So if each of those modules in this example is 4 volts, you'd add those together and have 16 volts. Okay. Now, I'll say a little bit here about the way these can be connected. The example I just gave you was connecting in series. If you connect in series from the positive to negative terminal of each module, you're going to sum the voltage up. Now, if you are stringing it together for other applications, you may want to keep that voltage low. There's other reasons to do that as well. But if you hook these modules up in parallel, you think of the newer Christmas lights that you get now. When one of those bulbs burns out, your whole system keeps producing. Let's say with the PV, if one of those modules was damaged, your system would still be operational, but in a series, you're going to have some impact to your system overall. But what I'll say, if it is hooked up in parallel, in this case, your voltage is not being added up. In this case, your current, your amps are being summed up. So in this case, each module is 5 amps. If they're hooked up in parallel, it's 5, 5, and 5 makes 15 amps. So there's a difference in how you connect those as well. Here's just for a reference for what an array would look like on the rooftop. In this case, you have 8 modules hooked together, 250 watt panels, making a 2 kilowatt system. So we have a little bit of time left, and again, if you're still typing in your questions, please continue to do so, and I'll answer those as we wrap up at the end of the session today. But now we'll kind of start to touch off on some of the types of systems. We looked at the basics last week, but we'll look at some of the other components of a system as well. The PV silicon panel, or whatever material it is, that's obviously the most important part of the system, but there's a lot of other pieces that work together for a system to operate effectively. I'll start just by highlighting the very different options of off-grid and on-grid or grid-tied. And I mentioned some of those last week, but with the off-grid, if you're going to use that, if you're going to have electricity available at nighttime, for instance, well, your PV is not working at night, so you will probably have something like a backup system, a generator, or a battery system to store that energy. When you are tied to the grid, you're connected to the utility lines, and so that would be the source of your power during, of your energy during downtimes. So a little bit difference there, but I do want to re-emphasize a point that there's usually a misunderstanding on this to some extent. If you are tied to the grid and you're using PV to supplement your energy, if for any reason the utility line goes down from a storm event or from work being done on the line, your PV system will also shut down. And so you'll be without utility and without solar, and that's a safety feature that's required by law, that your PV system is deactivated so you're not backfeeding energy onto the lines, which poses a significant risk to anyone working on the system. So just to reemphasize that, now you can combine these systems, and we'll look at some examples. You can have batteries and be on the grid, and we'll kind of analyze that. I'll just share briefly a couple applications, starting with the most basic direct type system. In this case, you have your module directly connected to a load, and the photograph I shared is a bilge pump pumping water. So very simple. When the sun is shining, you're producing electricity that drives the bilge pump, your DC load. That's a very simple example. There's limitations with that, of course, but that's basically how it works. Now, when we get more of the battery-based system, we're tying not only a battery into it, but you also have to have a charge controller. I'll mention a little bit more detail on that later, but the charge controller really protects the battery from failure. That's a critical thing to have in the middle there. But this allows you to store the electricity on a battery where at nighttime or when the sun is not active, then you can still run a load. Off-grid systems then are, what I mean by this is a little bit larger system typically, and you are then not only using it for DC, for the direct current, but also alternating current. And again, that goes back to where we started the presentation today, looking at the difference between direct and alternating AC and DC currents. And to do so, you'll need the battery bank, and these can be tied together in series, but you also need an inverter. And what the inverter does is take that direct current and translate that into alternating current that you can then plug a device into, like any kind of standard power tool or lamp or whatever it may be. You can plug into that. And there's a couple examples of your small scale inverters there on the presentation. Now the Grid Connect system, this is with no batteries. This is just directly tying to the grid, and so you're either using that electricity directly for your own AC loads, or you're sending that back to the grid, or pulling or pushing or pulling that electricity, depending on specific conditions. Here's a practical example of what that would look like with a rooftop system. You have that inverter that ties in with your breaker box, and then you have going either to your own uses, your own AC loads, or going onto the transmission grid. A Grid Connect interactive system combines the best of both, and so you get the battery storage and the electric utility all in one. And so this is becoming more common. There's a lot of interest in lithium-ion batteries for residential, but there's a lot of other applications as well. But you have your own storage for sustainability and resiliency, but you have electric utility as well. So you have multiple options with that type of system. Hybrid system would incorporate another energy source, so it is possible to have not only PV, but a generator or even wind turbine. And there's a lot of examples across the state of Maryland that have implemented this effectively on smaller to bigger scales, but being able to tie that multiple technologies in is growing in popularity and in function. So as I mentioned, I'll touch on some of the other components of a system. We do not have time in one webinar today to discuss all of these technologies, but we'll introduce some of these and then get into specifics on system design in subsequent webinars. So if you're able to join us for webinars next week and the week following, you'll start to get more specific, but I'll touch on those now. So the first would be looking at the mechanical side, just the racking and mounting systems available. There are, no limit to the different options that you have available for mounting. I shared a couple examples. The one on the left is for roof mounting systems, whether it's on your home or a barn or poultry housing, different options available. This particular example is flush on the shingles, and then you take an L bracket and the actual lag bolt goes through the roof, and so you have to be careful that water doesn't penetrate that system and into the trusses of your roof. But that's one example, and the railing then connects between those L brackets. Next example is a pole mounted system, and in this case it's a smaller scale system just for one or two modules. This has a concrete footing in the pole, and your conduit's running down through the ground and through that pole. This particular example of pole mounted has a mounting system at the top where you can rotate the angle. So in the winter, you'll have a higher angle on that and you can manually adjust it, or you could have a tracker on it as well. Ground mounted systems, and I'll kind of touch on some of the larger projects, not necessarily utility scale, but it could be. These systems are commonly, nowadays, they're using a pile driver or some kind of screw system to drive the post down into the ground, and then you build your framework on top of that. There's other options as well, concrete footers, and that used to be kind of a standard with a lot of companies using concrete footers. For these, it is a bit more expensive than the pile driving systems I just mentioned. ballast as well. If you weigh it down with blocks or something like that, you'll see that used on flat roofs. There's benefits. You don't have to penetrate the roof. You could use ballast on the ground as well, but you don't see it as often. Now, shifting gears into some of the electrical components, I've mentioned a couple of times the inverter, and that's what's taking your DC, your direct current from a PV system or battery, and translating that into alternating current, where you'd use in a house or a barn or whatever it may be. There's many different types of inverters. There's larger string inverters, and there's smaller micro inverters. There's a couple examples of what a string inverter looks like, and I'm not going to advocate for any particular company. I'm just sharing some images so you get an idea what they look like, but they come in a lot of different shapes and sizes. With a string inverter, each string series of panels is connected to an inverter, and then you can combine all those together. So in this example, you have 3 series string together, and so an inverter on each of those, having a total of 3 inverters. Here's what an example of a microinverter would look like, and in this case, you have a very small microinverter attached to each module, and that's growing in popularity. I think it's like 40% of the market now is microinverters. In any sense, inverters are a big expense, a big part of your PV expenses, probably around a quarter of the cost of the module itself. So it is a big piece of the puzzle. And there's a lot of options out there, and we'll look at some of this moving forward in subsequent webinars. Battery systems would be important if you're storing any of that electricity. There's many options out there for batteries as well. We will spend an entire webinar just devoted to batteries later this season. There's everything from your lead acid batteries, what's typical of, you think of a golf cart battery, to more expensive lithium ion at higher amp hours. And you'll see companies like Tesla and others producing those lithium ion batteries. So there's benefits, but it's also, for some of these battery systems, like some of the lithium ion ones, could be rather expensive. But we'll touch on some of that at a later time. As I mentioned, a lot of applications, you're going to tie the batteries together to have more than one. It really just depends on what you're trying to do. The charge controller is important as well. I mentioned this previously, but a charge controller really protects your battery from being under or overcharged, so it's not going to fail. There's 2 main technologies out there. There's the pulse wave modulation and the MPPT, which is more popular now and has its benefits. For one, you're able to send more power directly to your system, and it gives you a little bit better control over the size of the panel matching the battery. But again, we'll talk about this at a later date. There's other aspects of the system. We don't really have time to get into all of these today. I want to make sure we have time for questions, but briefly just mention there's a junction box tied onto the back of the panel. Typically, the leads are already wired into it. All you have to do is connect your cables to it. And for a lot of applications, you're going to need a master electrician to do this. But if you're looking at some systems, you can do it, or if you're a do-it-yourself kind of person, there's options out there. What you'll see most common is these MP4 connectors. Those have a locking mechanisms. You need a little tool to unlock them, the male and female ends, but those go on the end of your cable. We'll look at it at a later time, looking at the gauge and size of the cabling, kind of like your USB cables, but you're going to have a little extra shielding on these cables, and that'll protect it from environmental conditions. Wildlife or livestock could still get through, chew through that wiring. So it's not, an invincible wire, no matter what the gauge is, but I don't recommend putting goats around those, but that's some of the other pieces there. All of this has to be tied together and put into a system. There are the DC and AC disconnect switches to shut the system off. And so you'll have DC on the DC side, AC on the AC side. Combiner boxes are another technology out there that you'll be able to bring all of those. If you have multiple strings all coming together, combined in that box, to then go into a single cabling on the output side. So we'll talk about some of that again moving forward. There's different monitoring and metering systems from being able to monitor your battery. It's often a good idea to know the health of your battery and PV meters to measure output from your system. But we'll start to wrap up here. You know, all this information we've covered today is kind of helpful as we move forward and we start matching up our energy load to the PV panel that we design, our PV system that we design. And so, you know, in this case, it's a simple example of matching a bilge pump to your PV panel, but we'll get more complicated designs as well. Here's a couple examples of what that might look like is, you know, as you pencil out some of your thoughts on what you're hoping to accomplish and fitting all these pieces together, whether it's DC, off-grid, or alternating current tied to the grid. So